Where is the graph discontinuous and why? So take a second, maybe pause the video and answer that for yourself. But looking at it, we see that there is a discontinuity at 1 because there's a break in the graph. And we call that a hole, but more specifically a removable discontinuity because the point has been removed. So it's not continuous because if I draw the line, I'll have to pick up my pencil to leave a hole, and then I'll have to start the graph again. So every time you have to lift your pencil for a break in the graph, it's not continuous there. As we continue to draw this graph, we go to 3, and then we have to jump up here to continue the graph. So this is called a jump discontinuity. A jump discontinuity because there's a break in the graph. Then we continue to draw the graph and we have a hole and we remove that point and we move it up here. So this is again a removable discontinuity at 5. And then we would pick up drawing again after 5. So we've got discontinuities at x equals 1, x equals 3, and x equals 5. Looking at these functions, if I plug in, we want to find discontinuities. Well, we would see at 2, there is a 0 in the bottom. So that is a discontinuity. If you were to factor the top, you get x minus 2, x plus 1, and the x minus 2 will cancel the bottom factor. So if you are able to cancel the thing that gives you 0 in the denominator, that is a removable discontinuity. It's because it will create a hole in the graph if the bottom factor cancels. So here is the same function. Remember, that is an open circle, a hole in the graph, but we're filling in that hole at 1. So again, this is a removable discontinuity. B, if you were to look at this graph, you're going to see that it has an asymptote at 0, and then they're going to fill in that point at 1 on the asymptote. So this is, because there's an asymptote, it is called an infinite discontinuity. And then even though there's a point there, we have a break in the graph. If you remember greatest integer function from last lesson, you know that this looks like stair steps, and so you're going to have discontinuities at every integer, and they are going to be jump discontinuities because you're jumping from one line to the next, or one stair to the next stair. The definition of continuity is a function is continuous at a number if the limit of the function is equal to the value, the function value, at that x value. So the limit is what's approaching from the left and the right. And if the function actually equals the same thing as the limit, then we know the left and the right went to the same point, and we know that point must be filled in there. If they're not equal, that means you've got a hole in the graph, and the point has either been removed, or is just, it has been moved, or it's just been removed. And if you were confused by what I said on any of those functions, here are pictures to show you. So removable discontinuity, infinite discontinuity, removable discontinuity, jump discontinuity. A function is continuous from the right at a number a if the right-hand limit of the function equals the function value at that a value. A function is continuous from the left at a if the limit from the left of the function is equal to the function value of that a value. So let's look at this function and determine its continuity. So we see that it's a piecewise function and the only breaks in the graph are at 0 and at 1. So my potential discontinuities are at 0 and at 1. To test whether 0 is a discontinuity, we have to plug 0 into the left side, the left piece, plug 0 into the right piece, and see if they are equal. So let's do that. So in order to test continuity at 0, you need to look for these 3 things. You need to look at what happens to the left of 0, what happens to the right of 0, and what happens at 0 itself. So to the left of 0, we look at the piecewise where we look at the piece where x is less than 0 and we plug 0 in. So if I plug in 0, I get 2. If you look to the right of 0, you plug in where x is greater than 0 and you're going to get e to the 0, which is 1. If you want to know what happens at 0, you plug in 0 to where it says equal to, and you're going to have e to the 0 equals 1. So what this tells me is these two pieces don't match up. So we've got a jump discontinuity at 0. Jump discontinuity at x equals 0. Now, if I asked you, is it continuous from the left? You would say no, because the left limit does not equal the function value. If I asked, is it continuous from the right at 0? The answer would be yes, because the right-hand limit equals the function value. Let's consider limits at 1. So we know that there's two pieces broken at 1. Got a piece here and a piece there. So this piece is when the x's are less than 1, so to the left. This piece is when the x's are greater than 1, so to the right. So if I want to find my limit to the left of 1, I would plug in 1 to the left piece, which is going to be e to the 1, which equals e. If I want to know what happens on the right, I plug it into the right piece, which will be 2 minus 1, which is 1. And if I plug in 1, I want to plug it in where it says equal to, which would be this e to the x. So e to the 1 equals e. So what we see is, since the left side and the right side limit do not agree, there is a jump discontinuity at x equals 1. If I asked you, is it continuous on the left? You would say yes, because the left-hand limit equals the function value. If I ask, is it continuous on the right? You would say no, because the right-hand limit does not equal the function value. One of our important theorems is this one right here, and what the main part that I want you to know is that polynomials are continuous everywhere. We use this a lot in our proofs. You also see rational functions are continuous everywhere where they're defined. And then here's a list of things that are continuous in their domains. But polynomials are the ones that are always, always, always continuous. The intermediate value theorem. Suppose that a function is continuous on the closed interval a to b, and let n be any number between the y value for a and the y value for b. And these y values should not equal each other. If that is all the case, then there exists a number c between a and b, between your interval, such that the y value is equal to n. So that means such that the y value is between these y values. So if we have a continuous function with two x values, there's an x value between those x values that is between their y values. Here's an example. We've got x equals a and the y value for a. We've got x equals b and the y value for b. We've got a continuous function, which is this blue curve. There must be a x value between a and b that has a y value between f of a and f of b. Here's another one. In this case, there are three x values between a and b with y values that are between f of a and f of b. In this case, we've got a continuous function with a and b, and right here is a c, it's just not labeled, where the x value, it has a y value that is between f of a and f of b.